सेक्रेटरी साहब मिनिस्टर साहब बिजी हो गए हैं, मेंबर सर्विसेज साहब इनॉग्रेट करेंगे, आप शुरू कर दीजिए और अनाउंस भी कर दीजिएगा। शुरू करें?
Shall we start? Yes. Respected member services, DCC, Sri A.K. Mittal sir. Respected Mr. Hiroshi Ota, Advisor ITUT. Respected DG NTI-PRIT, Sri U.K. Srivastava sir. Eminent learned speaker in the session, Professor Anand Srivastava from IIIT Delhi. Professor Abhishek Dikshit from IIT Delhi. Professor Varun Raghunathan, IISc Bangalore. Mr. David Brinkley of Google LLC. Dr. Nagendra Nagaraja, CEO QIPAI. Sri Subhendu Sharma, founder of Wi-Fi Dabba. Senior officers and colleagues from DOT headquarters, LSA, TEC, BBNL, MTNL, BSNL, and other units. Researchers, accommodation, startups, students from technical institution and applied sciences, fellow colleagues from NTI-PRIT, ladies and gentlemen. Very good morning to all of you. On behalf of NTI-PRIT, I, Raju Sinha, DDG Transmission and NGS, welcome you all. We assembled this forenoon in the National Workshop on second version of Advanced Optical Communication. This workshop was scheduled to be inaugurated by Chairman DCC and Secretary Telecom, Sri K. Raja Raman Saab, but due to last minute engagement and very important meeting, he has sent his blessing to the workshop, and his absence, Sri Mittal Saab has kindly acceded to inaugurate the workshop. This workshop has 3 sessions: inaugural, that we are currently in, technical session, and parallelly going question and answer session when the learned speakers ends his presentation. May I request DG NTI-PRIT, Sri U.K. Srivastava sir, for his welcome address. Over to you, sir.
Thank you. Thank you very much, Mr. Sinha. Good morning to you, ladies and gentlemen. I extend a very warm welcome to our member, Digital Communication Commission, Mr. A.K. Mittal, who has kindly agreed to inaugurate this webinar or workshop on advanced optical communications. As Mr. Sinha said, our Secretary Telecommunications was to inaugurate and bless this event, but due to some engagement, he has not been able to attend. But all the same, Mr. A.K. Mittal has always been supportive to NTI-PRIT, and I'm very happy that he is inaugurating this webinar. So, welcome once again, Mittal Saab. And I also welcome Mr. Hiroshi Ota, ITUT advisor for Study Group 15, who has kindly agreed to deliver keynote address from Geneva. We are really thankful to him for his early morning presence in this workshop, and his presence today will enlighten us about the latest focus of ITUT in the field of optical communications. So welcome once again, Mr. Hiroshi Ota. I also welcome Professor Anand Srivastava from IIIT Delhi, Professor Abhishek Dikshit, IIT Delhi, Professor Varun Raghunathan, IISc Bengaluru, Mr. David Brinkley, Google LLC, Dr. Nagendra Nagaraja from QPI, and Mr. Subhendu from Wi-Fi Dabba. Then there are a lot of officers joining today from CDOT, Telecom Engineering Center, the LSI units, the Department of Telecom, officers from Telecom headquarters, academia, industry, welcome to you. Welcome to all of you and good morning. Ladies and gentlemen, we conducted a workshop on 10th March this year on the same topic, and that workshop discussed about developments in the optical transmission system manufacturing and availability of the systems in the country. The video of that event is available on our YouTube channel for your reference. In today's workshop, our focus is on various research activities ongoing in academia and industry in our country, especially on free space optics. Let me introduce the topic to you. The free space optics communication technology uses invisible light beams in free space, meaning the air, vacuum, or the outer space to provide high-speed wireless connectivity for telecommunications and computer networking. It's also called free space optics, FSP, or optical wireless transmission. The technology enables optical communications by transmission of modulated infrared light beams through the atmosphere. Unlike fiber optic communication that transmits data through an optical fiber, the invisible light beams are transmitted from one place to another using low power laser light and are collected by highly sensitive photon detector receivers, which will eventually transmit the digital data to the computers. So the free space optics communication technology is a low latency technology, and its light speed through the air is up by 40% higher than through the fiber optics. As per the recent market analysis by Emergent Research, the global free space optics communication technology market is projected to reach a staggering $4 billion by 2028, registering a revenue of CAGR of 33.3% during the forecast period. So this technology option is being viewed for providing last mile connectivity in 4G and subsequently in 5G deployments. I'm sure that this event will provide way forward for further discussions in this area. So ladies and gentlemen, once again, for welcome and thank you very much for joining this workshop. Thank you very much.
Thank you, sir. It is a matter of pride. We are privileged, and KPI is privileged, the nation as well, that Mr. Hiroshi Ota, advisor ITUT, straight from Geneva, is with us today. Sir, it is a great pleasure to see you this morning. Mr. Hiroshi Ota joined ITU in 2009. He is currently serving as advisor for ITUT Study Group 15, which develops standards on networks, technologies, and infrastructure for transport, access, and home. He also supports ITU WMO UNESCO IOC Joint Task Force on a smart submarine cable system. He coordinates the work of disaster relief and emergency communication with ITU and with related organizations. These were just few lines. There are many paragraphs to narrate about him. But paucity of time, may I now request Mr. Ota, sir, for his keynote address. Over to you, sir.
Okay. Thank you, Mr. Sinha. My name is Hiroshi Ota from ITU, and I'm happy to join this workshop and happy to introduce the activities of Study Group 15. So for my presentation, I'd like to use a slide. So let me share my screen first. Okay, so do you see the screen?
Yes, sir.
Okay, this is, so I'd like to introduce Study Group, the activities of Study Group 15, which works on the network infrastructure and develop standards on that. And for this period, I'm happy to welcome a vice chairman from India. Okay, and this slide summarizes the mandate of Study Group 15. In short, it develops telecommunication standards on network infrastructure, but it can be broke down as you see on the screen. So it works on optical transport network for general, and there are also developed standards for gigabit copper transmission, which is the access technology which uses an optical fiber up to some points before very close to a customer. Then it reuses a copper wire which is already installed for the usual telephone, so that you can enjoy broadband access without putting a hole in your building, just reusing the existing wire. And Circuit 15 also works in various areas of technologies, such as equipment and maintenance aspects, and the management of network elements. And also it works on the optical fibers and cables, the related installation. This means it works on the outside plant. And Circuit 15 has some 3 lead study group roles on, as you see on the screen. It's access network transport, home networking, and optical technology. And lead study group means it coordinates activities with other organizations. And since these technologies are worked by not only by ITUT study group 15, but also standardized by other groups such as IEEE or Broadband Forum and so on. So the study group 15 takes a role of leading. So it doesn't mean study group 15 does everything, but the study group 15 coordinates with other organizations with these technical areas. And study group 15 is divided into 3 subgroups, which is called working parties. And these are working party 1 works on the access and home networking. Working party 2 works on the optical technologies itself, optical fibers and outside plants. The working party 3 works on transport network characteristics, and it works on how to use optical networks, or how to structure the signals input to optical fibers. Next 3 slides highlight some work in each working party. And working party 1 works on broadband access, and it's divided into optical access and copper access. Copper access means it reuses the existing copper wire, and optical access means using optical fibers up to the end of the access network. So the end users use directly optical fibers to enjoy broadband access. And it's already mentioned, free space optical transmission is also a topic to be standardized, and the study group 15 works on this technical area for the home networking application. So it is called visible light communication, and it uses the light source usually used as a lighting, but also used as a source of the signal at the same time. And the home networking area also uses power line and other wires to realize the broadband communication within a home. Next, Working Party 2 works on optical technologies, and it works on the infrastructure and outside plant, as well as dense wavelength division multiplexing to carry more and more optical signal by a single fiber. And as you see, short reach 200G and 400G interfaces are also developed by reusing the Ethernet applications. Working Party 3 works on optical transport network, and they're working on the support of 5G mobile and beyond 400 gigabit per second interfaces and network synchronization. And they also work on the management aspects of control and transport planes. These are the outline of the mandates of each working party. And I'd like to introduce some of the achievement done so far, again, from each working parties. And Working Party 1 achieved 50 gigabit per second capable passive optical networks, which is called, abbreviated as HSP, which means higher speed passive optical networks. And the passive optical networks means optical access. And this technology uses passive element outside the telephone offices to divide one optical fiber into several, 16, 32, or up to 64, to be shared by many customers. That's why it is called passive optical networks, or abbreviated as PON, PON. And there are several other items listed here, such as 10 gigabit capable symmetric PON, optical access, or higher speed bidirectional access, and radio over fiber systems, which is mainly used for connecting base station to the next station for supporting 5G mobile, and copper access, as I already mentioned. These are called G.fast fast initially, up to 2 gigabit per second, but now they are also working on MG fast, which means multi-gigabit G-fast, which aims at up to 10 gigabit per second, even using copper lines. And the home networking are also listed. And at the bottom, there are visible light communication means free space optical transport. And in bracket, recommendation numbers are indicated. So these are, since these are already achieved items, it's already available as recommendations. And from ITU homepage, recommendations can be downloaded. And in case of PDF, it is free of charge for everybody. So I invite everyone to read any recommendations of your interest. In the same way, Working Party 2 achieved several recommendations as listed here, such as single mode fiber recommendations. They are long-standing continuing work, but the single mode fiber is most important optical fibers for long distance transmission. And also the transmission using optical amplifier as listed in second bullet. And multi-channel bidirectional dense wavelength division multiplexing application is also standardized. They also worked, for example, third bullet from the bottom, criteria for optical fiber cable installation with minimal existing infrastructure. So not only developing the state-of-the-art technologies, Sargu 15 also develops optical fibers suitable for developing countries, which means easy to deploy, or for example, not instead of putting a trench and bury the fiber, L.163 and also companion recommendation L.110 specifies a fiber which can be directly placed on the surface so that the installation can be done very easily. And also it is an application of the submarine cable technology to make the optical fiber very strong. For example, it survives even if it is run by a car over an optical fiber. These are also standardized. And working party 3 worked in the network hierarchy and multiplexing technologies as listed here, and also synchronization and management are also standardized. So, and then again, a bit busy slide continues, so sorry for this. But these next 3 slides list the future work. So if you are interested in providing your proposal or any interest, I invite you to consider participation of Sargu 15 meetings or other activities. You can participate in a meeting, but also you can just subscribe to a mailing list or in the field of your interest so that you can see the discussion on email. And many communication between experts are also done in mailing list. So subscribing mailing list allows you to see the discussion in specific areas of Sargu 15. And interim meetings are also happening. Currently, most of the meetings are held virtually. So in a way, it is easy to participate in a meeting compared to the physical participation. And this slide lists the future work for Working Party 1, which is the access area. And there are several items ongoing. Some are overlapping with the achievement because many items are ongoing, and also there are some technologies are aiming at even higher speed or even wider application. And as you see, there are passive optical networks, optical access, or MG-FAST, which is a access technologies using existing metallic cables, and other things using UHD video or higher speed fiber-based premises and transceivers, which is optical fiber technologies deployed in a household. The same way, Working Party 2 has many feature work items, and there's, for example, first one is space division multiplexing transmission, which is a technology to put many cores in one optical fiber so that the more broader transmission can be realized. And I'd like also to highlight 4th and 5th bullet from the bottom. These are scientific sensing submarine cable system and also scientific monitoring and telecommunication submarine systems. These are technologies to monitor the temperature, pressure, and movement of deep sea water. And the result of the measurement can be used for monitoring the climate change and also detecting the movement of the Earth. So it alerts tsunami beforehand so that it gains time to evacuate for the people to be hit by tsunami. And these are realized by putting scientific sensors to the repeaters of submarine cables. So this is a different technology from telecommunication, but this is realized using optical fibers and G.dot Smart scientific monitoring and telecommunication submarine systems, which is called smart cables. This is a combination of measurement of deep sea water and telecommunication, so that those functions can be realized with lower cost. Working party 3 future work items are listed here. Again, they in general work on multiplexing method itself. See, it is called interface specifications and architecture and restoration protection, which is a combating technology for the network failure. Even in case of network failure, so that telecommunication can continue. And the network synchronization and the network management is also studied. So the many items, but in summary, study group 15 is leading development of standards on optical transport network, access network, and home networking. So in general, network infrastructure standards are developed by study group 15, and it's a large group and very productive. It produces 30 to 50 recommendations at each meetings, which happens every 8 months. And the highlights include home networking and broadband access and transport technologies. So these are the summary of study 15. And in general, you can easily search using the word SG15 or study group 15, or maybe if you could add ITUT study group 15, then it hits many of the related web pages. And from study group 15 web page, all the information is available. And the next study group 15 meeting, which is the first meeting in this study period, 2022 to 2024, happens in Geneva, 19th to 30th of September this year. So if you're interested, or I also would like to invite to participate in this study group meeting to participate in development of telecommunication standards. So with this, I'd like to conclude my presentation. Thank you very much.
Thank you, Mr. Hiroshi. We feel very fortunate to listen to your inspiring and very informative keynote address. You have truly given insight into the working party's achievements and future work being carried under SG15. This really shows the achievement and future work really show how it is going to impact our planet in communications. Thank you so much again.
Thank you very much.
We at NTI are delighted to have member service DCC who accepted our last minute request to inaugurate the workshop. May I now request member service Sri A.K. Mittal sir for his inaugural address and to declare the workshop open.
Thank you, Mr. Raju. Shri UK Srivastava, Senior DG NTI PIT, Mr. Hiroshi Ota, Advisor ITUT, Subgroup 15, the speakers for this technical sessions, and all the participants. Secretary Telecom was to inaugurate this workshop, which is being organized on the topic, very important topic, the role of optical wireless communications technologies. It is advanced optical communications. The topic is very important, and I am indeed privileged because the last minute change in the program, I am honored to inaugurate this workshop. Indeed, we are privileged to witness the transformation of India into a digital nation, harnessing the potential of new age emerging technologies such as 5G, artificial intelligence, IoT, big data, M2M, etc. is the key to this change. In fact, these technologies are new age carriers of growth for all sectors of the economy, including education, healthcare, financial services, logistics, agriculture, and manufacturing, etc. Like any digital nation, data consumption in India is rising exponentially. Monthly data consumption per Indian subscriber has increased from 0.1 GB in 2014 to approximately 15 GB as of today. Thanks to the rapid growth in penetration of broadband services, proliferation of smartphone usage, declining trends in data tariff, and pandemic also has helped this scenario. To support this historic transformation, a robust, scalable, low cost, and high bandwidth transmission has become imperative. It is in this background the optical communication has emerged as an unavoidable option for high-speed transmission of information across the globe. In perfect synergy with the advent of World Wide Web, big data transmission and processing, video communications, or high-speed, high-definition, on-demand entertainment, the capacity of optical communication systems has experienced a steady and rapid growth over the years, adapting to the ever-growing requirements of the society. India has embarked on one of the world's largest rural optic fiber rollouts in the world, aiming to connect 6 lakh of its villages to the broadband. The convergence of a cluster of revolutionary technologies, including 5G, AI, IoT, and data analytics, promise to accelerate and deepen its digital engagement, opening up a new horizon of opportunities for advanced optical communication. The implementation of new technologies like 5G, IoT, and M2M, etc., will be crucial in deploying intelligent solutions for smart cities, which demand robust and high-capacity optical connectivity across the city for their efficient operation. Deployment of advanced optical communication systems shall cater to these future digital growth and innovation requirements. A robust competitive landscape in this area will ensure availability of new communications, technologies, services, and applications, which is central to the growth of GDP, productivity, and creation of new jobs in the economy. I am happy to share that the Department of Telecom has constituted a task force in January 2022 for formulating the roadmap for advanced optical communications in the telecom sector in India. The task force, which has already started its works, consists of eminent persons from the academia, industry, and government. It is to formulate a white paper on deployment of advanced optical communications. Committee is also working with international standard bodies and alliances in advanced optical communications to enable development of standards appropriate to India and to assist Indian IP to find place in such standards. It will also support startups in research, design, development, and commercialization of advanced optical communication products and services. In the workshop organized on 10th of March, as was highlighted by my colleague Mr. Srivastava, by and large, the discussion was focused on how to create core infrastructure for welcoming upcoming optical communication revolution. Today's workshop on advanced optical communication is in continuation of the same. Today's workshop is likely to throw light on the state of our technologies to utilize the same for increasing throughput with lower cost. This will be highly helpful in sensitizing all stakeholders in the matter of national importance. Even members of the task force are attending this workshop to get better insights. I convey my best wishes for the success of this workshop. With this, I declare this webinar open. Thank you.
Thank you, sir, for your inspiring address and thoughts, wherein you have elaborated the importance of today's topic of advanced optical communication and its relevance. Following the keynote address and your inspiring words, it has really set the tone of the workshop. The relevance you have stressed upon in its use, either through optical fiber or through free space communication, which will support many networks, which will further help mankind through its uses and economic growth of the society across the globe. Thank you very much, sir. So now we have come to an end of this inaugural session. First and foremost, I would like to thank Member Services, who, despite his busy schedule, has spared his time and joined the inaugural session at a quick request. Secondly, I would like to thank Mr. Hiroshi Ota for sparing his valuable time to attend the session and guided us even to join SG 15 meetings taking virtually at various occasions. I would also like to thank our DG and head NTI-BIT, Srivastava sir, who has been great source of inspiration in formulating this workshop and its first part, and always guide in making activities meaningful. Thank you all. Now we'll move to the technical session, wherein we'll start the presentation based on the addresses we have listened so far. For this technical session, I would like and request my fellow colleague, Director Transmission, Sri Subhas of NTI-BIT, to conduct and host the session. Over to Subhas.
Subhas, you are muted.
Okay. Thank you very much, sir. So let us start our technical session. In this technical session, the first speaker is Professor Anand Srivastava from IIIT Delhi. So Professor Anand, sir. Just let me. Okay. So let me introduce him. Then by the time he will be joining. Yes, Professor Srivastava, please, sir. Most welcome.
Okay, so thank you very much. Let me share my screen and please let me know if you are able to see my screen.
Yes, sir, just give a minute time so that I may introduce you formally to the audience, sir.
Okay, please.
Professor Anand Srivastava, sir, he is from IIIT Delhi, from electrical. Yes. Before joining IIIT Delhi, he was Dean and Professor in School of Computing and Electrical Engineering at IIT Himachal Pradesh and also adjunct faculty at IIT Delhi. Prior to this, he was Alcatel Lucent Bell Laboratories, India as solution architect for access and core network. Before joining Alcatel Lucent, he had a long stint, almost 20 years with C. as director and member of C. Board. During his education, majority of projects were completed successfully and commercially deployed in the public networks. He was also closely involved with IT Geneva in Study Group 15 and represented India for various optical networking standards meetings. His research work is in the area of optical core and access network, vehicle-to-vehicle communication, fiber, wireless, this 5i and architecture, optical signal processing, and visible light communication. So, Mr. Sir, Professor, sir, please over to you, sir. You may proceed, sir.
Okay, thank you very much. Let me share my screen first. So are you able to see my screen? Hello?
Yes, sir. Yes, sir.
Okay. Just let me know the slides are also moving, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, thank you very much, and thanks for inviting me. So the topic is role of optical wireless communication technologies in beyond 5G and 6G. What are the prospects, what are the directions and challenges? So briefly, I will discuss what is actually beyond 5G or 6G vision, and what are the different optical wireless technologies, and then what are the building blocks required for optical wireless technologies, and what are the further research directions, and then what are the challenges ahead of us, and then finally I'll conclude. So just quickly going through the evolution in the generation of land mobile radio communication network, we have come long way from 1G, 2G, 3G, 4G, currently in 5G, different trials, commercialization.
Sir, please switch on your mobile, this mic, sir. Sir.
Is it okay now? Or did I?
Yes, sir. Yes, sir. Fine, sir.
So did you miss my earlier part or?
No, it's okay, sir. Yes.
Okay. Okay, so yeah, so different releases are coming. Right now we are around at release 16, and the basic aim of 5G is to have massive machine type communication. We are talking about 200,000 devices per kilometer square, and also looking at enhanced mobile broadband speed of the order of 20 gigabits per second, and also the latency is going to be less than a millisecond.
Sorry, there is a lot of echo. Can we fix this?
The echo is coming from my side, or I'm not, I don't know.
I don't know, but there is a lot of echo. I'm not able to hear.
Is it
No, I think audio is okay, Doctor.
I think Abhishek
Okay.
probably looks
Abhishek
like.
can rejoin. He should log out and join perhaps.
Okay, sure. Yeah.
Okay, so I'll continue, and the reliable low latency communication of the order of 1 millisecond. So this is what 5G is, and so 6G, what is the vision? The first thing is it is going to be a global coverage, which is basically a space, air, ground, and sea technology, which will cover satellite communication, which will cover UAVs, terrestrial network, and also integrate with the maritime or the network which is inside the water. So this is going to be an integrated technology of space, air, ground, and sea, which actually 5G, this integration was not possible in 5G. And also it is going to exploit all spectra So we have seen sub-gigahertz and millimeter wave, and a lot of work has happened in terahertz. And now, as these frequency bands are getting exhausted, the next switch is to optical, and my talk is going to be around this optical spectrum, how the technology is shaping up using this optical spectrum, and also to make the network more manageable and more automated. You require artificial intelligence and big data. So this is also a part of 6G vision. And then one is looking at a strong security both at the physical layer and the network layer. So 6G wireless communication, 5G, as I mentioned, was basically mobile broadband, enhanced mobile broadband, which is EMBB, and massive machine type communication, which is MMTC, and ultra reliable low latency, which is URLLC. But 6G provides, the combination of these two. For example, mobile broadband, reliable low latency is not only low latency communication, but also it offers high efficiency, reliability, and speed. Some of the applications they require all these features, for example, XR, whether it is AR or VR, or brain-to-computer interaction (BCI), or connected robotics and automated systems. They all require, combination of mobile broadband, reliability, and low latency. And also, you require, along with low latency, a massive ultra reliable low latency communication. So this is a combination of reliability and massive type machine communication to provide higher quality and reliable services, for example, smart factories. And then there's one more concept which is coming up, which was not there in 5G and earlier technologies, is quality of physical experience, which is actually a new term, and it combines with the quality of service and quality of experience, and it also gives a physical experience of the human itself. So basically, this will have experience of human. There have to be some parameters which will define the experience of the human, along with the quality of service and quality of experience. And then finally, it is going to be 3CLS and energy services. For example, when I say 3CLS, is basically communications, computing, and control. These are the 3Cs. And then it will also, exploit localization information, sensing information, and also you should be able to get energy from the wireless energy transfer. So the 6G is going to have a convergence of these 3CLS and energy services. So just to tell you the spectrum which is available in optical domain, you can see here IR, visible, and some part of ultraviolet which can also be exploited. And if you see this spectrum, which is in the IR and visible range, is actually 2,600 times what is available in the RF domain. So optical spectrum will have the potential to serve a large volume of data traffic generated by high data rate heterogeneous multimedia applications which are required for 6G and IoT applications. So these are some details about the spectrum. As you see, RF is extending from 3 kilohertz to 300 gigahertz, and whereas optical is from 300 gigahertz to 30 petahertz. A factor of about 3,000 times in optical domain. So, and it consists of IR, VL, visible light, and ultraviolet. And within IR, you have far infrared, thermal infrared, and all those details. Within visible light, you have red, orange, yellow, green, blue, and violet. Similarly, in ultraviolet. So the spectrum is huge. So there is no scarcity of spectrum. The limitation comes from somewhere else. So basically, OWC technology, which will be used for 5G and IoT, are mainly 4 types. One is visible light communication. It is more at the physical layer, that is point-to-point communication, which uses light emitting diode and laser diode at the transmitter, and then you have a photodiode at the receiver. So this uses visible light, and this is going to be a bidirectional. And Lifi is similar to Wi-Fi. So it has both downlink and it has uplink. It has it can handle handover. It can support user mobility. and downlink is visible light. The uplink is going to be, could be a combination of infrared or visible light or ultraviolet, or it could be a Wi-Fi in uplink. So all those possible combinations are possible in Li-Fi. And the third is, using optical camera communication, or OCC, where you use array of light as transmitter, and then the camera of your device, whether it is a whether it is a mobile handset or some device which has a camera. So this also has some applications in 5G beyond and Internet of Things, which is optical camera based or optical camera communication. The fourth one is free space optics, wherein you can cover a large distance of the order of few kilometers and at a speed of few gigabits per second, and it uses laser diode as a transmitter and APD or pin diode at the receiver, and the transmission is either in the IR range or the visible light range or ultraviolet range. So these are the four basic OWC technologies which will be used in beyond 5G and IoT networks: VLC, Li-Fi, optical camera communication, and FSO. Just to give a brief comparison of these four technologies, for example, VLC is going to be unidirectional or bidirectional, depends on the scenario. Li-Fi has to be bidirectional because there has to be upload as well as download. And OCC is, most of the times it is unidirectional, and free space optics is again bidirectional, or it could be unidirectional. And the communication distance for VLC is mainly limited inside a room, 20 meters. Li-Fi is of similar order. OCC can give you a distance 60 meter, where FSO, it has been used in space, and people have used few thousands of kilometers as the distance. And the mobility support in VLC can be made optional but limited. Li-Fi has to support the mobility, and OCC is again optional. FSO is primarily a point-to-point technology, so there is no mobility support. Environmental effect indoors, there is not much environmental effect indoors. Li-Fi, again, it is an indoor technology. OCC, again, indoor technology. And free space optics is outdoor technology, so environment is going to have some effect on the communication performance. Interference level in VLC is low, Li-Fi is low, OCC is almost zero, FSO is low. The data rate which you can get using VLC is about 100 gigabits using laser diode, for example. With Li-Fi, people have achieved 100 gigabit using diffused laser diode. With optical, the speeds are not very high because of the limitation coming from the camera side, but still 50 plus megabits can be achieved. And free space optics of the order of 50 gigahertz at distance of few kilometers has already been achieved. Security, being in technology inside the room, is high security. Li-Fi is on similar lines and high security. OCC is also high security. FSO is also point to point, can be considered as a high security communication system. So if you see the applications of OWC, it ranges, basically from millimeter distance to thousands of kilometers. So, for example, let me use a laser pointer. So suppose you want to communicate between two chips, high-speed communication, which is of the order of few millimeters. One can use a miniaturized laser transmitter and laser receiver for communication between the chips. So this is ultra short range. And similarly, you have short range, wherein you have body area networks or personal area networks or underwater communication or communication within the flight. So they fall under the short range category. One can use OWC technology. Then there is a medium range, which is about 100 meters or a few hundred meters, vehicle to vehicle communication, or vehicle to, for example, traffic light communication, or indoor communications. These are some of the examples of medium range. And in the long range, you can use free space optics as mobile backhaul, connecting your system with some backend switch using mobile backhaul technology, uh, using free space optics. And then you can always use free space communication between two satellites or from satellite to aircraft. So all these things have been demonstrated. So as you see from this slide, this OWC can find anywhere, can find application anywhere, starting from a millimeter distance communication to thousands of kilometer communication. This is some example of VLC, for example, in space. This is the air network. This is underwater network. And then you have a terrestrial network, vehicle-to-vehicle communication or backhaul links. And also inside the room where you have Wi-Fi or millimeter wave and visible light communication. So you find this OWC technology in all parts of the areas. So they can be basically classified into 4 parts: low speed, short distance as mobile communication, positioning. There are some examples: low speed, long distance, underwater network or vehicle to X, sorry, or high speed, long distance, private network or space network, and high speed, short distance, for example, medical communication, security communication, and ultra speed, short distances, indoor high speed access. This is an example of how light communication can be used in underwater. Right now, underwater, you have options like acoustic waves or RF waves, but they have certain limitations. So if you want to communicate with underwater, with some sensors or some underwater human activities, diver want to communicate with some underwater vehicle. So all these communications are possible using visible light, and it can be integrated with the main, terrestrial network or, network on the ground. So just to tell you the earlier technologies, RF and acoustic, they had certain issues. For example, RF, the distance is also not very high, and you require hundreds of watt of transmit power. The cost is very high, and you can't achieve more than 100 megabits. And antenna size requirement is also quite large. The latency is moderate. Acoustic can go a long distance, 20 kilometer, but the speed is very, very low. So your data rate is of the order of few kilobits per second, and you require few tens of watt of transmit power. Antenna size is about 0.1 meter. Latency is very, very high in acoustic. Whereas in optical, right now, the communication distance is not very high, of the order of 50 meters. But the speed of light is high, so you can have high speed communication up to gigabits. People have demonstrated about few gigabits, a distance of 50 meter in underwater, and the power requirement is also not very high. Few watts are required. The latency is low. So if you want to have longer distance communication inside the water, then one has to rely on relaying and self-configuration of the network, self-organization of the networks. You should also support mobility. So all these things, there are some challenges still if you want to consider optical for underwater communications. So these are some of the challenges are mentioned here. So basic building blocks required for OWC network is actually you start from devices and components, and then there are some optical front-end systems. Then one has to study different channel models, and one has to know what are the different data transmission techniques, and then the MAC protocols, and how do you mitigate interferences, and networking and protocol standards. So the devices and components, I mean, the spectrum is huge, as I explained earlier, but then the devices, they have limited bandwidth. So the challenge is to develop devices which have got very, very high bandwidth. And if you want to exploit the bandwidth at some 250 megahertz or 350 megahertz, then the kind of emission wavelength you require is few nanometers or sub nanometers at at visible light. So the requirement is very, very tough. But if you can get high bandwidth devices, then you can exploit the spectrum to your advantage. Optical front-end systems, I can't use laser because sometimes laser is not eye safe. So one has to use diffused laser. I have to ensure that eye safety standards are met, and I have to also care about the mobile terminal, because the terminal is not stationary. It is not always facing the light. So I need to worry about the orientation part and ensure that whatever the orientation is, you are always connected. Large area detector if I use because I want to correct light coming from different parts, but then the capacitance of the detector will increase, which will actually, decrease the response time of the detector. So in order to mitigate that, I need to use some concentrators, and concentrators also the gain is limited by that by denominator which you see here, sine square theta, that theta has to be very, very small, which means it has to be almost point to point or aligned communication. So there are pluses and minuses of using detectors or use of concentrators. In order to handle all these things, one uses angular diversity transmitters and receivers. So there are multiple receivers at different angles so that you get light from all possible angles. Channel models is another challenge because the light is coming from different paths. So there will be good understanding of line of sight, non-line of sight component is required. What is the temporal spread of the reflected signals? Some signal is directly coming, which is line of sight. Some are getting reflected, traveling a longer path. So there will be some temporal spread. And then reflective to the materials, what kind of wall you have. It is a painted wall or it is a wooden wall, or what is the reflectivity of the material, and whether you are designing your system for industry or for a room or for a hall. So those kind of scenarios also need to be understood. So one has to characterize the channels based on all these parameters. And then there are different data transmission techniques for OWC. Intensity modulation direct detection is most common. Then people also started using coherent. For example, in FSO, use of coherent OWC system, which gives you additional advantage. On-off keying, and if you want to further increase the data rate, one uses advanced modulation techniques which are spectrally efficient, for example like OFDM, and then cap, carrierless, and amplitude phase modulation. Also one can exploit spatial dimension and wavelength dimension. When I say spatial dimension, basically I'm referring to multi-input, multiple output. You use multiple transmitters and multiple receivers. And also if I can use multiple wavelength, I can exploit wavelength dimension for high data rates. So there are a lot of research which is going on, exploiting these techniques to get high data rate. The another one is medium access control, whether you want to use TDMA or OFDMA or CSMA-CA. Ultimately, you have to worry about what is the throughput, what is your queued packet delivery probability. So these are some of the metrics which one has to worry about. And if I see some of the recent representative and advances which are happening in the last decade, there has been a fast development. So you can see, for example, using RGBI somewhere here, you have one has achieved 15 gigabits using red, green, blue, and yellow lasers. So it's a WDM system for free space optics. And then 2.5 has been achieved using some technology. So basically, and for underwater, a good amount of speed has been achieved using light emitting diode, and also using micro LEDs, you can achieve a higher data rate. So there has been a good progress in the last, I would say, 5 to 6 years in terms of all these OWC technologies. But still a long way to go when you want to exploit very, very high speed. So one has to work on materials and devices for VLC systems. For example, for transmitter, there are different LEDs, silicon LEDs or SLDs, superluminescent diodes or micro LEDs. These are all high speed LEDs. So one has to exploit these LEDs for their advantage. And then similarly on the receiver, you have SPADs, you have multi-pixel photon counters or LSC, luminescent solar concentrators. So there are different kind of receivers, and ultimately you have to combine this transmitter and receiver into a transceiver. And in future, technologies like amplification or modulation, muxing, demuxing, they will also be part of OWC technology. So challenges what we have is, right now we have limitation of the bandwidth of the light sources and detectors. So one has to look for high bandwidth light sources with new materials and new mechanisms. Silicon-based detectors are mainly sensitive to infrared, so high responsivity detector based on different materials, single photon detectors. Use of SX for VLC is currently not there. One has to work on design of SX, which will have all these functions, AFE, TIA and all those baseband processing, and point-to-point communication. If you want to increase the speed, one has to use MIMO techniques and exploit wavelength dimension as well. And also I should be able to do some beam forming. So there are some optical IRS which are being researched, which will help us in beam forming towards the user. So these are the challenges which still scientific community has to meet. And also there is going to be a lot of machine learning applications in visible light communications. So there are a lot of things like nonlinear mitigation and channel estimation and jitter compensation. So there are various techniques in machine learning algorithm which can be exploited for handling this nonlinear mitigation, jitter compensation, and phase estimation and things like that. So challenges of the OWC is frequent handover, because there are many light sources inside the room. You have to frequently hand over. Intercell interference, there are different attocells, they might interfere. There is some atmospheric loss if you are considering, for example, free space optics. Uplink, still there is some challenge. Downlink, there is no issue, but uplink still there is a challenge because you have to rely on IR or Wi-Fi. OCC, optical camera communication, low data rate because of the camera is also area of research, flickering, and then data rate improvement for all these systems. So in conclusion, VLC is going to be a potential technology for 5G and 6G technology platform. Some technical aspects which make VLC is elegant choice is, one can use heterogeneous network, a combination of Li-Fi or Wi-Fi. One can achieve high data rate using, for example, micro LEDs, and it promises, good security. So they're all requirements of 6G use cases. However, there are, challenges in terms of interference, issues with ambient light. Handover is an issue which should also be attended to. Intercell interference, backbone design, and going beyond a few 10 gigabits or 100 gigabits. So these are some of the challenges. Still, this technology is work in progress, but I'm sure in next 5 to 6 years you will see deployment of these technologies in some way in the network. So thank you very much. This is all from my side. I hope I have stuck to the time of 20 minutes. Over to you.
Yes, sir. Thank you, sir. Thank you very much. So in this, if you have any question, you may please ask, or you may write in chat box also right now. If you have any question from Professor Anand Srivastava, you may ask right now. Okay. So let us switch to our next speaker. Our next speaker is Professor Abhijit Dixit from IIT Delhi. He will be delivering talk on advancement in optical wireless communication technologies. Professor Abhijit Dixit, MTech in Optoelectronics and Optical Communication from IIT Delhi, and PhD in Computer Science Engineering, INTEC, Ghent University, Belgium in 2014. Since 2015, he has been an assistant professor at IIT Delhi, where he has taught courses related to optical communications, signal processing, communication engineering, and networking. He has also taken an NPTEL course on principles of digital communication. He is leading research activities at IIT Delhi in the area of optical communication and networking. He has also carried out several consultation projects in the area of railway signaling. He has published over 30 international journal articles, including IEEE, JSAC, IEEE Common, Magnum Journal of Light Wave Technology, Journal of Optical Communications and Networking, IEEE Networks, IEEE Transactions on Network and Services Management, and over 50 publications in international conferences. Over to you, Abhishek sir. Please proceed.
Okay, thank you. Am I audible?
Yes, sir. Yes, sir. Please proceed.
My slides are also visible.
Yes, yes.
Okay. Okay, thank you, respected Chairman, sir, and all other distinguished panel members. First, I would like to thank National Telecommunication Institute for giving me an opportunity to make this presentation. As the title of my presentation is Optical Wireless Communication, but in this presentation, I would like to focus on developments at IIT Delhi. Okay, so it's more confined to. So I would like to talk about two solutions. First, in the area of free space optical communication system, which is basically an outdoor technology. And then I will talk about Lifi networks, which is basically an indoor technology. So let us start by talking about free space optical communication system. So what is a free space? As some of you may already know that we have FSO transmitter and FSO receiver, and these typically are installed at the top of a building or a mountain and anywhere you feel like. And typically a transmitter has a data source, it has a modulator, it has a laser, it has a telescope or optics, and the receiver also has similar components. So we have a photodetector, amplifier, and a decision device. So this is a technology which can provide excellent data rates, and this should be used whenever laying of fiber is not possible. So sometimes we have difficult trenches, and then this technology has its importance. But there are also several demerits of this technology. One of the demerit is it has to be line of sight. So the transmitting and receiving telescope should be oriented towards each other. Then there is effect of atmospheric turbulence. So we can have scintillation, which is the variation of received intensity versus time. We can have beam wandering effect. So you can see that the beam may not be reaching the receiver, right? So we can have beam wandering effect. And then there can be a beam spreading effect also, where the beam spreads, right? And typically, because of beam spreading, the received power at the photodiode becomes smaller. So these are some effects which poses challenge for FSO communication system. Not only this, there are also weather effects, right? So if because of these weather effects, there is a significant attenuation in FSO system. So typically, if I see the power flow in fiber, this offers much less attenuation with respect to length versus FSO, where the attenuation is very high. And this is because of weather effects, because of high scattering, and so on and so forth. So there are certain demerits of FSO communication systems also, right? So in this talk, we are going to talk about.
Abhishek, I'm just seeing the title slide. I don't know it is true for me or for everyone. I'm just seeing the title slide here.
Is it true for everyone?
No, sir, it is changing. I am able to see the whatever topic he is saying. Sir,
okay, I'm just seeing the title slide. Okay, I'll try to.
Please check just network connection on your side, or otherwise you may leave and rejoin, sir. That will.
Okay, okay. Please go ahead. Sorry to disturb. Okay.
Yes, Abhishek, please proceed, sir.
No problem. So here I'm just showing you how the BR performance. BR performance is an important metric for digital communication links. So how the BR performance of FSO communication system is just due to scintillation. So if I just consider scintillation effect, no attenuation, no scattering losses, nothing like that, just focus on BR performance of FSO communication system due to scintillation. Then if I look at the high turbulence regime, when the turbulence is very high, then what you can see, to get a low BR, for example, 10 to the power minus 5, I need an SNR of 65 dB. Now that is a huge requirement on SNR, and no communication system would be feasible with such a high SNR requirement. If I look at the moderate, still the requirements is quite high, 45 dB, and in weak, the requirement is around 18 dB. So these are very high numbers of SNR requirement or EBNO requirement. Both are interchangeable quantities for an FSO communication system, depending upon the turbulence level. And this is one of the major challenge why FSO communication system is not commercialized, and there are a lot of roadblocks in the deployment of this technology. So how to get rid of this effect, how to get rid of this scintillation effect, that is my focus. So let us try to use some error control codes. LDPC, low density parity check codes, are very good codes for 6G communication. Let us just try to use these low density parity check codes. What do we see? We see that there is no change whatsoever. There is some minor change, but the gains are not significant. That means error control codes does not work well for FSO communication system. And this is because the data rate is much higher than the coherence time of these channels. So typically the coherence time of FSO communication systems is larger than 1 milliseconds, and data rate is typically larger than 1 Gbps. So because of these two things, the FSO communication system is a slow fading channel. And we know that the use of error control codes for a slow fading channel doesn't give us any advantage. And that's what we also see here. Now, what we can do is we can use LDPC with interleaver, right? And we can use LDPC interleaved in different turbulence regimes. And here we see significant improvements. So the SNR requirement in high turbulence regime reduces to 35 dB from 65 dB, and that is a good gain. But remember, what does this interleaver do? It requires or it induces a lot of delays in communication systems. So if I am talking about 1 millisecond, interleaving length is typically chosen 100 times of the coherence time. So we are talking about the delays of 100 milliseconds, and which is not acceptable again from 6G point of view, right? So the moral of the story is LDPC interleaver is good, but at the penalty of delays. So to remove these impacts, what we have done is we have used this idea of channel assisted coding. So we have filed a patent on this as well. So in channel assisted coding, we have used in concatenation with LDPC codes, or in combination with LDPC codes, we have used this channel assisted coding. So what we do is we have received the bits from the LDPC encoder, but now we first sort the bits in the order of their degrees. Degrees in simple terms can be understood as so if I'm looking at the degree of a bit, this simply means how many other bits this bit influences. OK, so that's the degree of the bit. First, I sort the degrees of the bits, and then the bits with the lowest degree is transmitted to the channel with the highest coefficient. So I use multiple channels here, and these channels are indexed by H1, H2, Hn, and so on and so forth. So H1 is the highest channel coefficient. So I transmit the bits with the lowest degree to the channel with the highest channel coefficient, and this gives wonderful results. Remember, this is not MIMO. MIMO normally sacrifices on the spectral efficiency, but there is no penalty of spectral efficiency. There is no other penalty. It simply increases cost because now I am using multiple channels. But we know from our experience of MIMO, MIMO is a very acceptable solution, and this is similar in cost like MIMO, but it doesn't have any penalty of spectral efficiency. So when I use this CAC scheme, and if I simply choose the number of channels as 2, and here I compare the results with interleave, the best results that I had earlier. So these dashed lines, which you can see, are from LDPC interleaved solution, and the solid lines are the CAC solution. So in CAC, we have reduced the SNR requirement to about 23 dB compared to 35 dB in LDPC interleaved. So this is a very good solution if we are looking at the commercial feasibility of FSO communication system. But we can also choose an bit higher. We could have chosen it to 64, and there what we see is SNR requirement or EBNO requirement drops down to 10 dB. So it's a significant achievement. Remember, earlier we were thinking about the SNR requirement of 65 dB. Now we have reduced this to 10 dB, which is a very good solution. OK, with no sacrifice on spectral efficiency and other penalties. So this is our solution on FSO communication. We have also verified this through an experimental link. So we have built an experimental link at IIT Delhi. We have also built a turbulence generator chamber. So using these components, we have been modeling the heating effect by having a heater in this turbulence chamber, and we used a fan also to model the wind speeds, etc. So we have a fully functional OTG which can simulate turbulence of different kinds, high, moderate, and low. And using this setup, we have also characterized the performance experimentally. Now we will talk about the Lifi network solutions. So I will not go into the details of what is a Lifi. I think this has been introduced by Professor Srivastava. So I know you understand this. I will like to pitch in the most important application of Lifi. Lifi most important advantage is you can form very small cells with LED lamps, which has a higher directionality compared to a Wi-Fi router. And because of these very small cells, the solution is very scalable. For example, if this LED lamp gives around 100 Mbps, and I can have around 100 LED lamps covering the entire hall, then I can go up to 10 Gbps. I'm just assuming a very pessimistic number of 100 Mbps, right? So you must be considering these numbers very pessimistic after the presentation by Professor Srivastava. But even then, the total data capacity is very high, 10 Gbps. And this is definitely much more than the capacity of a Wi-Fi network. And that too at safer wavelengths. So visible lights are considered much safer than the other frequencies. So it's a scalable and it's a safe solution. So there are also certain challenges like dimming support. You need to switch off the LEDs and still talk. You should not make LEDs flicker. You should be able to get good data rates over these LEDs link. And this is I will be presenting a small demo of the Lifi link, which we have done in IMC 29. So we should be able to get good data rates over these Li-Fi or LED links, and we should be able to communicate without interference. For this, we will need MAC protocols and multiplexing schemes. So what are our achievements in terms of the devices? So we have shown a Li-Fi link up to 3 meters, and we have got a bandwidth more than 80 megahertz. So this is quite a recent result from our team. And so 80 megahertz will mean that if I use 4Com, I can go up to 160 Mbps. And of course, this bandwidth is achieved with blue filtering and with equalization circuit, proper equalization circuit. Receiver sensitivity is also good, about 0.1 milliwatt. So in this demonstration, I will show the multiplexing as well. So earlier I just showed a point-to-point link, but now I will present a video demonstration with TDM, time division multiplexing over Li-Fi. And I will also show that the receiver is mobile. Earlier the receiver was quite stationary. Audio there on the presentation? Can you hear the audio? I think Hello, am I audible?
Your voice is audible, sir, but no voice in presentation.
Oh, sorry.
Your voice is very clear.
Okay. Just give me a second.
No voice, sir, again.
So I will just speak through. So here I was showing that there are two Li-Fi receivers and a single transmitter. A single transmitter is transmitting signals for two receivers. And so you can see the received signal on these computer screens. And yeah, there was no problem in receiving. And next part of the demo, that move the receiver. So which here, yeah, even if we move the receiver, that is Wi-Fi systems, the life receiver location. So we can move the receivers in a radius of around 3 meters also. So this gives us some motivation to make these systems. Okay, so also we have developed a lens system which was giving us a good acceptance angle and a lateral tolerance. So earlier the results were up to 2.4 meters, but now we have increased this up to 3 meters. Okay. So I will not show the demonstration. This demonstration I will skip with the lenses, but of course all these listed can watch them. So we have also developed a multiplexing scheme which is NOMA based, and we have called this multiplexing scheme fair power allocation, which gives much better performance than the state-of-art schemes that exist in the area of VLC. And you can see that in fair power allocation scheme, the sum rate is increased a lot. Then we have also combined the VLC with the RF. So here I have assumed the VLC link, and between user terminals, I also assume some RF link. And based on these two links, I can increase the reliability of the entire system. And this system is known as CONOMA. So CONOMA definitely has a much better performance than a single NOMA system. So we can see here that the outage probability is much reduced. So these are some significant achievements from our group in the areas of Lifi. We have also developed a MAC protocol. Again, I will not show the demo in the interest of the time, but the main idea is our own developed MAC protocol is much better than the standard MAC protocol. So we can see a much significant increase in the throughput, around 100% increase than compared to what exists in the standard. So our MAC protocol is full duplex, whereas in the standard it is not full duplex MAC protocol. So I skipped this demonstration also. So we have developed, I think, I'm not sure, but I think we have developed fastest Li-Fi system in India on white LEDs, right? So over white LEDs, we have achieved 160 Mbps with a distance of 3 meters. We have developed the lens systems to track and focus light coming from different angles into photodiodes. We have got a good lateral tolerance of around 3 meters, and we have developed the entire software stack for the Li-Fi network. We have a downlink and uplink link. Uplink link is working on RF and IR both. So we have developed two solutions, and we have shown the multiplexing of multiple users inside the LED. And this research has led to several 2 patents and 8 journal papers and 10 conference papers in this area. So this is it. If you are interested, you can go and look at the publications which explain these things in much more detail. So you can look at the patents, you can look at the journal papers, we can look at the other papers, conference papers. There are a lot of publications by our group in this area, and if you're interested, you can look at them. So I conclude my presentation. If you have some questions, I would be happy to answer. Thank you.
Thank you, Professor Abhishek. Anyone having any question, you please ask him. Please raise your hand, or
I'm not able to hear you.
So let us proceed to next session. So next session will be taken by Professor Varun Raghunathan from ISC Bangalore. His topic is laser-based high-speed indoor visible light communication. Professor Varun Raghunathan received his PhD in electrical engineering from University of California, Los Angeles in 2008. Thereafter, he worked in different capacities in USA. He worked in one startup also, postdoctoral researcher, and also he was a research scientist. All these three in USA. Finally, in 2016, he joined ISC as an assistant professor. His research interests are in free space optical communication, optical meta surfaces, non-linear optics, and optical microscopy. Over to you, Professor Varun sir. Please proceed, sir.
Okay, thank you very much, and I would like to thank the organizers for inviting me to give this talk. So today I'll be talking about some of our work in laser-based optical wireless communication, which is geared towards indoor applications. So this is the quick outline of what I would like to talk about. First, I will give you a quick motivation for why use lasers for indoor optical communication. What are the challenges associated with using lasers for this? And then I'll also give you a general overview of what a block diagram of this communication system looks like, what are the basic components and so on. And then I will move on to talking about our research work. My group mainly works on optical system development for next-gen VLC and optical wireless communication. So we are an experimental optics group. So we look at different implementations of optical communication links. And in particular, I'll talk about two applications what we have looked at more recently. One is a blue laser, which is down converted to white light, and it's used in an indoor VLC link. And the second is an hybrid LED and a laser transmitter combined with beam steering for indoor optical wireless communication. So this has already been covered in the previous talks. VLC is finding a lot of interesting applications for indoor uses. Either it could be something like an office space or more in terms of maybe like a hospital setting or a power plant, for example, where RF or microwave is considered as an interference and would not be allowed inside such a setting. Or even it could be an airplane where the reading lights could be used for doing communication as well. But for most of these technologies still, right, for example, in the office space or even airplane type settings, VLC is always competing with Wi-Fi technology. And there needs to be a compelling reason why VLC needs to be used in lieu of using Wi-Fi. What is going to be the key differentiator, right? That's where these use cases like hospitals and power plants and all come in useful. But going even beyond that, where could be the real benefit of using VLC or optical wireless communication in general? So if you look at what are the driving forces behind using optical wireless for indoor application, it's really the data rate which is available per user. Right? It may not be distributed in an entire room where the data rate is being distributed across multiple users, but maybe the real advantage comes in where the gigabit or whatever be the high data rate that's being offered to across a small cell, right? And there are commercial products which are currently available in the UK, in Germany, and also in India as well. There are companies who are working towards this. But if you look at the technology trend, where I show you the different transmitter technologies as the x-axis and what kind of data rates are available, right? So initially this used to be a single LED, for example, then it used to be multiple LEDs, for example, the RGB LEDs. So this has essentially pushed the data rates from megabit per second, tens of megabit per second to all the way to few gigabit per second, where there are multiple LEDs being used, and also there needs to be a lot of emphasis on the modulation formats. The electronic front end has to be that much more complex to support the kind of data rates which need to be supported by the LED. But looking ahead, right, what is being done beyond a few gigabit per second, one has to resort to high bandwidth light sources. And in this context, there is interest in micro LEDs, for example, and even beyond that, there is interest in laser diodes to do communication. So why use laser diodes for communication? Laser diodes offer a very high bandwidth. I'll talk about this a little later in my subsequent slides as well. But lasers are also an important technology or an upcoming technology for illumination. Right? This is a spin-off company out of UC Santa Barbara where they are looking at blue laser diodes to do illumination. And if you see these kind of technologies, right, at the heart of it is a blue laser and a phosphor, which down converts this light to generate white light. And this technology is being currently used in commercial applications as well. One example here, which is shown, is a high-end car in Europe. This is a BMW, where the headlights are essentially laser-based headlights, which are the laser is being converted to white light to do the illumination, basically. Right. So this technology is upcoming. There are applications or there are consumer uses which have been identified. And the next natural sequence is that this can be used also for indoor illumination as well. But things are not that easy, because when I start using lasers for indoor uses, there are a few things that need to be considered. One of the main consideration is the eye safety, right? I'll talk about that in a subsequent slide. The other point when compared to LEDs is that one needs complex current or temperature control. What is the cost of realizing these structures and so on, that those need to be considered as well. So before I move on to more details about the transmitter, what does a typical link look like? This is a very simple cartoon of what this link would look like. There is a transmitter, which could be a laser or an LED, which is being down converted to white light using what are known as phosphors, which are also a diffusive surface. And then the beam starts spreading out, and then there are suitable lenses which are used in front of the transmitter to guide the light towards the receiver. At the receiver, you would again have condenser lenses to collect the light and then focus it onto a receiver. The receivers could be, depending upon the bandwidth, this could be PIN or APD detectors. It also depends on the sensitivity as well. Right? So this, any optical wireless or a VLC link would look something like this only. So the innovation comes in terms of what kind of light sources you use, or what kind of optical lenses you use, or what kind of receivers you use, or in the electronic front end or the modulation formats, which are not shown in this picture. So if we look at the light emitter by itself, there are two choices, right? There could be an LED, which is an incoherent source of light which starts spreading out all over the place, or a laser diode, which is more directed, which is based on stimulated emission, and it could be guided over long distances, right? And this basic physics mechanism, right, whether it's spontaneous or stimulated emission, has a consequence in how they behave, right? The light output as a function of the drive current is very different for these two. Right, I could get this large slope in the light as a function of current for the lasers, which is not possible in the case of an LED. So with a small current modulation, I can efficiently transfer it to light output, which is often difficult to do in the case of an LED. Having said that, there's also other things that need to be done to guarantee that this slope is very high. I need to temperature control and current control this device, which requires additional investment in terms of the mount and the controller, which goes to modulating these devices. The other big advantage which comes in because of the underlying physics is the modulation bandwidth. In the context of lasers, I can achieve easily a modulation bandwidth of gigahertz, if not tens of gigahertz easily, because it's based on a stimulated emission process, which is very fast. In contrast, when you look at LEDs, the modulation bandwidths are limited to tens of megahertz, and then you have to apply equalization or some pre-emphasis, de-emphasis in the communication front end to make sure that these bandwidths can be extended, but not by too much, right? You cannot push it to a gigahertz, which is difficult to do, right? So our interest here is to make use of lasers, which inherently offer a high bandwidth, and by making use of that, the electronic front end can be simplified a lot, and then use this combination to do indoor optical wireless communication. But what about eye safety, right? I want to use lasers for an indoor setting. So there are standards which are available on how much laser can be used in an indoor setting. There are, so for example, there's an American National Standard Institute, ANSI, they have published some standard intensity levels where it's safe to operate across some time duration. And these are typically called as maximum permissible exposure. So if you consider a blue laser, you will follow this green curve here, which follows the visible wavelength range. So for a long, prolonged exposure, the laser exposure has to stay below about 0 dBm per centimeter square, or about a 1 milliwatt per centimeter square is what is permissible. So this typically, the reason why you have these kind of safety limits is because when you have this directed laser beam, your eye itself can act like a lens and focus this light onto your retina, basically, right? So when this happens, your retina can get damaged. So there are certain wavelengths which your eye lens will not pass through, which are typically called as eye safe. For example, the telecom wavelengths are considered to be relatively eye safe, that you can use higher powers of them and still transmit them across distances. So one saving factor here when we use this in an indoor setting are what are known as diffused laser beams, where if I try to kill the spatial coherence of the laser, then the laser is no longer directed, so the eye will not be able to focus that tightly onto the retina. So you can so these threshold numbers can go lower or go higher significantly, basically. So I can use higher powers if it is going to be diffused. That is so much for eye safety, but then that's not the only consideration. There could be skin damage also which could come in from lasers, so that also needs to be considered. But those numbers are typically even higher than eye. So eye is the thing which can get damaged rather easily. So one would focus on eye safety, but other parts of the body also need to be considered. So the same argument also holds good as you go to RF and or as you go to new frequency bands in RF and microwave, right? Even for 5G, people talk about, is this safe for human usage in a given setting? A similar discussion or consideration needs to be done for optical wavelengths as well. And as long as we keep the exposures below a maximal permissible limit and also make sure the light is diffused, it's generally considered safe for indoor usage. And that's what we have tried to do in our implementations as well. Then the other part comes in that if you want to use it for communication, that's where the high bandwidth comes in. But then when you want to use it for illumination, the next thing is that how do you quantify the illumination source? So there are standards again for this who quantify the illumination source. When you talk about white light, it has to be of certain quality. So whatever light source we build in our lab, we try to benchmark it against a standard illumination source and also quantify its color temperature. The lower the color temperatures are, typically the red the light sources, but the higher the color temperatures are, the bluish the white sources. So there needs to be a good balance that needs to be found when you want to use these kind of light sources for indoor illumination as well. So it's not just the communication performance which is important, but if it is intended for a VLC like application, then how good is the illumination also needs to be considered. So with that, I'll move on to talking briefly about our research work. So the first part of the work I'll talk about is where we have looked at the channel model, and then in specific, we looked at the path loss in the context of a blue laser down-converted white light transmitter, and then try to realize high data rates over a reasonably long link length. So this is the channel, essentially the optical system we have in the lab, where we have a transmitter, where we have a laser diode, which is being down converted to white light using a phosphor. That's where you generate the white light. And then there is a transmitter lens, which projects it towards the receiver. At the receiver, the light is being collected by the condenser and then focused onto an avalanche photodetector. So as you see here, this is an emission profile we measured directly coming after the phosphor, where you see this kind of a Lambertian profile, where the M value, which denotes like the larger the value of M, the more narrower the beam is. But we get a wider spread to this beam. That this essentially shows that the blue laser and the white light which are being generated are essentially we are made spatially incoherent, that you get more like an LED or a more diffused kind of a beam profile coming out of the phosphor. The next task was to do channel modeling, where there are already formulas which are known for this. This is well known. There is this typical 1/d square dependence, right, of how this light will decay as it propagates from the transmitter to the receiver. There are other factors which comes in because of the condenser gain and so on, right? But one more thing that needs to be appreciated here are the lenses which go in front of the transmitter and the receiver. So this formula, right, it's very well known even in antenna literature. So this is maybe as old as the 1920s or 30s, where you call it the Fry's formula in antennas, right? But then the fact that we are using lenses here makes this very powerful, because now I can design the curvature of the lens, or I can design the position of the lens with relative to the transmitter. And this gives me an additional degree of freedom to control the path loss. And the way we do this is by using a ray tracing model, where we start with a transmitter. We have our condenser lens, we have a transmitter lens and a condenser lens, and the rays which are propagating at different angles are being essentially collected by the receiver lens and focused onto the receiver. Then I can come up with I can essentially do a bookkeeping of all the rays which propagated from the transmitter to the receiver, appropriately scaling for the intensity or the Lambertian profile of the light which is being emitted. and then I can figure out how efficiently I collect the rays at the receiver. So this is one way of doing the path loss model where I propagate every ray, right? So this is more like a Monte Carlo method where every ray is being considered and propagated from the transmitter to the receiver to compute an overall path loss, right? This is a more simulation based model for the path loss rather than coming up with an analytical model where it's often difficult to also account for the spacing of the lenses from the transmitter or the receiver and so on. Right. So with this kind of a model, one can minimize path loss by playing with the transmitter and the receiver lenses such that the collection efficiencies can be maximized. In our example, for a link length of about 3 meters, we were able to achieve a collection efficiency of almost 1.7%. And this was very close to the theoretical limit. Like once I have a lens, right, I know the solid angle over which the light is being emitted. I know the area of the emission. So I know that the product of the area and the solid angle needs to be conserved. And that can be traced from the transmitter to the receiver. The ratios of those from the receiver to the transmitter is the best collection efficiency I can ever achieve. And that number was around 1.9 to 2%. And by just playing with these non-ideal lenses, we are able to achieve close to 1.7%. So we are close to what is being allowed by this, what is known as this Etandu limit, and the collection efficiencies were fairly good. And based on the lens position, now I can optimize for specific link lengths. If I want a very short length, I play with the distances to maximize the collection for that particular link length. Or if I want a long length, like for example 3 meters, then this can be played. So this is just by playing with the lens positioning, keeping the lenses fixed. So one could tailor the VLC link based on what is going to be the link length basically. Right. So with these kind of systems, we did more detailed characterization of the optical performance of this system. I'll skip some of these details in the interest of time. We also quantified how the light behaves in terms of its color content with respect to a standard D65 source and so on. And one more point is that we kept all these blue laser below the MPE limit by at least an order of magnitude to make sure that this is really eye safe if this at all is going to be used for an indoor VLC application. And with this, we were able to also demonstrate communication performance. So in this example, I show you simple on-off keying type modulation where data rates were pushed to as high as 1.5 gigahertz across a link length in the range of about 200 to 300 centimeters, so about 2 to 3 meters, which is typically practical for if you consider a transmitter on top and a receiver on a desk, for example. Those are the typical link lengths one would want to achieve for that. We also compared how this performs when compared to other implementations. We found that this makes use of the lowest light level, which was guaranteed because of the path loss optimization we did. The link lengths are not larger, but then these kind of data rates for this link length, the product of data rate with link length is one of the highest which has been ever demonstrated. So the last part of my talk, I'll talk briefly about this hybrid laser LED transmitter we recently worked on. What is the motivation behind it? I already told you lasers achieve the best communication performance, but then they are very harsh in terms of an illumination source. LEDs are very good for illumination. They are being widely used. They are considered green and all that, but then they are not very good for communication just because their bandwidth is very limited. So can we achieve the best of both worlds? That's where we started working on these blue laser down converted to white light. But then even that we found has some issues. Why I say that is because the communication and the illumination performance are always interlinked. If I want to achieve the best communication performance, I need a lot of blue light. That means the light source, the illumination is going to look more bluish, right? Which is not good for an illumination kind of application. If I compromise on achieving best illumination, then I get less of blue light. It's not good for communication. So what is the workaround around this? So can I consider decoupling the communication and the illumination performance? And that's where this kind of hybrid concept comes in, where you can pick any laser and any LED and put together a transmitter system with that. And even that is not sufficient. One thing what we noticed with all this path loss optimization is that the beams become more directed when compared to a standard LED which is being used for illumination. So obviously you need to do beam steering. And can I do it selective beam steering only for the communication light, right? That is another motivation where we started looking at this hybrid kind of a light source. So this is a block diagram. I wouldn't spend too much time on this. I have a demo video which I will show you later. But at the heart of it is a near IR laser which works at the 785 nanometer wavelength range, and an LED ring which is being used for communication. These two are combined at the diffuser surface. So the diffuser does the job of combining these two. And now I have separate control over what LEDs I use and what laser I use for doing the communication. And then to implement beam steering, we made use of two liquid lenses here. One of them is offset along the x-axis, the other is offset along the y-axis. So these off-axis liquid lenses, as I change the curvature of these liquid lenses by applying a voltage, these beams will steer basically, right? So I want to make use of non-mechanical beam steering using liquid lenses, and then this is done only for the laser while the LED is kept as it is. Then the other part where we wanted to also do was this closed loop beam steering. To do closed loop beam steering, what we did was to also embed a low bandwidth detector at the transmitter. The purpose of the low bandwidth detector was to essentially sense the light which was being transmitted. In fact, I can even sense only the white light which is being transmitted. And depending upon how off axis the receiver is, the signal will go down. And based on that signal information, I would be able to steer the beam basically. So using this, we were able to demonstrate closed loop beam steering as well. So this is a work which got published in Journal of Lightwave Technologies in 2022. So then we went on to characterizing the illumination and communication performance. Now, since I have control over the LED, I can choose a very good LED. So for this implementation, the LEDs were very close to the D65 source basically. And we also did communication where we implemented OFDM. And we also did bit loading where depending upon the subcarrier SNR, we were able to adjust the number of bits which are being transmitted. We also did power loading to make it more efficient communication. And with this, we were able to achieve close to greater than 5 Gbps data rate, where the inherent bandwidth, what you see here, right, for the link is limited to about 600 to 700 gigahertz, right? So with that kind of a limited bandwidth, we are able to push the data rates much higher using advanced modulation formats. For beam steering, as I explained, we made use of off-axis liquid lenses. So these are images we obtained with steering, where one can see that there is a slight elongation in the beam, which comes about because of coma effects, off-axis coma effects. But notwithstanding that, we were still able to achieve very good communication performance across a fairly large steering range. So this is about 40 centimeters along the horizontal axis and about, I believe, 10 centimeters along the vertical axis at the receiver plane. And closed loop steering was demonstrated, as I told you, using low bandwidth detectors. So let me quickly move on to showing a video of what we have. Hopefully this will work. I hope you're able to see this. So this is our hybrid LED laser transmitter. So this is the block diagram I've earlier shown. This is the link. It looks like the link length over which this was demonstrated is about 1.5 meters. And what you see here is essentially the transmitter consisting of the near IR laser. The modulation is coming. So in this example, we just used a simple on-off keying modulation, which is directly modulated onto the laser diode. Then there are liquid lenses which are used for steering. There's this LED which is used for illumination, the diffuser at which these combine, glass lenses which are used to direct this beam. At the receiver, we have a low bandwidth detector which is shown here. We have a receiver lens which is used to collect the light and focus it. Here we just use simple PIN detectors and oscilloscope to collect the data and process this basically. Right, we'll show one example of this real-time beam steering where I already showed this, where we are measuring signal strength, and based on that we lock to a specific position. So first, this is line of sight alignment where the receiver is placed at a particular position. Then the receiver is moved. So what you see here is the eye diagram goes down, and then the beam scanning starts. And from using the beam scanning data, the liquid lenses are locked to a specific position, and then you get back the communication performance basically. Right. This was demonstrated across an angular coverage of plus minus about 7.6 degrees basically. And the same thing was also done with OFDM also, but in the interest of time, let me just skip that and let me conclude. So where we work on is mainly optical system design for advancing optical wireless or even VLC links. Some of the ideas of interest to us in the past has been path loss optimization, building hybrid transmitters, and also demonstrate beam steering, right? And few points I would like to make is indoor VLC plays an important role, right, for communication, but then there is an initial adoption barrier that needs to be overcome. So definitely this kind of an initiative by DOT is most welcome in kind of getting the word out that optical wireless and VLC are important areas where we need to do research and R&D basically. The other part is lighting fixture manufacturers, the famous lighting fixture manufacturers like Philips and so on also have to gain adoption, or they have to start looking at communication systems more seriously as a value add to illumination sources. And standards also need to be established. So definitely the ITU initiatives are most welcome in that regard. Right. So let me stop here, and I will also thank DOT as for the funding as part of the 5G testbed project for some of the work I showed. If you're interested in learning more about the IISc 5G testbed, I've also given the website here. So let me stop here and thank you, and I'll be happy to take any questions.
Thank you, Professor Varun. If anyone having any question, please ask. Professor Sir is here. Please raise your hand if you want to ask any question. Professor Varun. Okay, so let us proceed to our next section. Our next speaker is Mr. David Brinkley from Google. He will be delivering talk on Project Tara. David Brinkley is the engineering lead of Project Tara, Google's monsuit to expand global access to fast, affordable internet with beams of light. Mr. David has been active in developing advanced optical communication technologies and products for nearly 2 decades. He previously led multiple Defense Advanced Research Project Agency programs, a high production multiple integrated laser integrated systems programs, and the wireless optical communication and hardware development on Project Loon. Over to you, Mr. David. Please proceed, sir.
Okay. Yeah. Thank you very much, and thanks for having me. Is everyone able to see my slides?
Yes, sir. Yes, the slide is visible. Sir, make it full screen. A slide show. Right now it is in PPT mode.
Great. Okay. All right. Yeah. Thanks again for having me. Yes, my name is Devin Brinkley, so engineering lead for Project Tara. And so I'll just do a quick overview of Tara's wireless optical communication system. I'll dive into a couple of the key subsystems, so the tracking system and then the digital communication system. Talk a little bit about capability we have of rate adaptation, which I think is a differentiator from other technologies. And then RF fallback, which is the extreme of rate adaptation. I'll talk about a little bit. And I've got some data for field performance. We've got hundreds of links out in the field for several years now, so we've got some good data to show there and good statistics. Okay, so just to start out, so Tara's mission is providing affordable and abundant internet, and we believe that wired solutions itself is not enough for this. So there needs to be some sort of wireless solution. And the problem is that the existing wireless solutions are running out of spectrum. So as you move up from microwave up to gigahertz, up to 10 gigahertz, and even 80 gigahertz, where 5G is at now, you start to run into some limitations, especially as you get higher than 100 gigahertz. Electronic efficiency drops off, especially for power amplifiers, and there's relatively high channel absorption from water absorption. So our solution is leapfrogging the RF spectrum and moving to 190 gigahertz, and a lot of advantages in this spectrum that a lot of people have covered so far. That we're leveraging a lot of the telecom industry. It's unlicensed, unregulated, and essentially unlimited spectrum in that region. So what does our solution look like? So you can see a couple of the terminals mounted on a deployment or on a tower at a deployment on the right. So this would be so it'd be 2 terminals mounted on this tower. There'd be 2 terminals on the remote side, up to 20-kilometer distance separation. I'll talk about that a little bit, but there's a trade-off for range and performance. We typically try to target between 2 and 15 kilometers, but we've operated even out to 50 kilometers range for some demonstrations. But you plug in essentially 2 fibers and in power. In the 2 fibers are 10 gigabit Ethernet connections. And in terms of the operator, it essentially looks like you're just plugging the 2 fibers together across the link. So a lot happening under the hood, a lot of link layer protocols that we take care of. But in terms of the end user, it's all transparent. And 20 gigabits per second, bidirectional, full duplex, so sending multiple wavelengths for each of those channels. And then the power connection could be PoE, could be DC power, and relatively low power consumption, similar to incandescent light bulbs. So 40 watts typical, max of 60 watts. And then the weight's 13 kilograms. This was a target based on being a single person lift, and then class 1M eye safe. And Varun gave some good information on eye safety in the previous presentation, but essentially unconditionally eye safe as long as there's not aided optics in the path. Aided optics being 50 millimeter binoculars or telescope. Okay, so maybe I'll walk through the optical path or trajectory through the system. So this is an exploded view of the terminal. In the core components, you can see here are the optical components in the center, and then the electronics on the right. And so walking through the receive, you have light reflected off this coarse pointing mirror, which I'll talk about a little bit in the next slide. And that passes through this beam expander, which in the transmit direction is expanding the beam. In the receive direction, it's compressing the beam. So it's compressing it from 70 millimeters down to just a few millimeters. So you have a few millimeter beam here, and then continue the path. You reflect off this fast steering mirror, which I'll talk about also in the next slide. And then you reflect off a fold mirror, and then a dichroic splitter that separates the tracking system wavelength from the comm system. And so the tracking system wavelength goes to a position sensitive detector, which provides feedback in terms of what the angle of arrival received is into the terminal. And that tells you which direction to point it back at the remote terminal. So that position's then fed back to the fast steering mirror. The mirror points at the remote terminal, and then with pointing the transmit at the remote terminal, the receive is also pointed to couple into the fiber. So now the receive path is coupled into the fiber, and that's kind of a key attribute of the system, because now that we're into fiber, now we can use standard telecom type products. So now we can pass through wavelength division multiplexer filters to split to multiple wavelengths. We can go through optical attenuators to attenuate the signal, and we can go into our relatively standard transceiver. That's a standard SFP form factor and just customized in minor ways based on some of the unique aspects of the wireless optical channel, but for the most part, just a telecom SFP. So then that's converted to electrical signal. It's passes through to our processor that then unpacks the data, takes all the link layer protocols out of the data, and then it's transmitted out as just standard 10 gig Ethernet. Okay, so focusing a little bit on the tracking system. So I mentioned on the previous slide, it's 2 components to that. So there's a coarse pointing mirror, which is taking care of the relatively slow motion. So this would be like a building drift over days, typically motions that are much less than a hertz type bandwidth. And then you have your fast steering mirror, which is correcting for tower sway or high motion tower or high dynamic tower motion based on wind on the tower, or if we're mounted to a rooftop, you could have like an HVAC that would have vibrations, but anything from several hertz out to several hundred hertz type frequency. And the fast steering mirror is covering a majority of the the motion, and the CPM for the most part, coarse pointing mirror for the most part is inactive, just for these minor updates to ensure we're maintaining within the fast steering mirror's field of view. So with the two of those together, we're able to achieve a pointing error RMS, so standard deviation of 5 microradians. So this pointing error is critical when we're talking about beam divergences and in the realm of 50 microradians, so 1/500th of a degree. So a good example of the tracking systems is histogram on the bottom. You can see with the tracking system disabled, we've got a standard deviation that's much larger than our beam width, so 160 microradians. And then as we turn on the steering system, it tightens up to this 3 microradian standard deviation. This tracking system is critical as we're when we're mounted on these towers, we see motions of 5 to 20 hertz type frequencies and motions in several degrees per second, which is if we're talking again about 1/500th of a degree, that's relatively significant and puts a lot of strain on the tracking system. So a lot of work's been done on this. One of the key features that we're currently working on for the next generation that's shown really good performance is adding an additional input of an inertial measurement sensor as an input and using that as a feed forward mechanism. So initially using low latency feed forward, and then having the additional correction of the error based on the position sensor. But we've seen that give relatively good performance for some of the higher dynamic towers. Okay, and another key subsystem is the modem, and there's two key features to the modem. There's a lot of different components, but just focus on the main ones. We have the forward error correction, which adjusts based on the channel conditions. So as the channel conditions degrade, we'll increase the code rate and lower the sensitivity, the effect sensitivity threshold. And then we have automatic repeat requests, which is critical. It's to ensure that the higher level protocols are not impacted by the link layer losses. So the ARQ will buffer up the data and then wait for acknowledgement to be received on the return direction before, and if it's not received, then retransmit it. So it's not guaranteed delivery because we want to bound the latency, but it for the most part ensures that the data gets across based on the typical link statistics. So a nice video demonstrations on the right that shows our digital comms engineer, Bruce Moyson, locking the beam, and you can see with the ARQ off on the right, that's impacting these higher level protocols, and then with the ARQ on, there's no drop data, and it's transparent to the user. Okay, so a continuation of the digital comm, we've recently started testing out rate adaptation. And initially, we're just adjusting the baud rate and moving from that 20 gigabit per second all the way down to 1 gigabit per second. And based on the dynamics we see for the link, where you have these slow power fluctuations, we were able to switch the baud rates at a rate much less than a millisecond. And we can change based on these changing dynamics. So as the power drops, we're able to change from 20 gig to 10 gig, and you can see so this is the data rate. You can see the sensitivity increased by 3 dB, and then move from 10 gig down to 1 gig, and then increase another 7 dB. So additional 10 dB of gain just with changing the baud rate. There's other rate adaptations that we have in works, but it's very early in development and looking at some of those for the next generation. This sensitivity here is based on some dynamics for the channel. Just FYI that this isn't the detector threshold, but the sensitivity based on a given channel condition. Okay, and then the extreme of the rate adaptation, again, would be the RF fallback, where again, if you're looking at the data rate changing versus availability, you can see that initially we had changed the walk data rate, so we changed the baud rate, increasing the availability from 86 to 92%, and then to 93% as we lower the data rate. And then the extreme is as we get down to less than a gigabit is to switch to RF, and at that point you're at essentially 100% availability. So it's a nice solution if there's links that you can send high priority data over the RF link, and you can guarantee the delivery, and then also get the additional capacity of the walk at the times when the walk is up. So this is a time series on the bottom here. It's showing sending 400 megabits of data, and you can see the walk on the top here is dropping out for a period and then switching over to the RF in the middle and increasing to the 400 megabits. And the key plots on the bottom here, we can see the aggregate data is maintaining that 400 megabits per second data rate throughout that period. Okay, so I mentioned we've got hundreds of links out on the field and multiple years of data from these links. So this is a plot. So anytime you're talking about wireless communication, it's always important to look at the availability. This is showing the availability versus range, and this is looking at only India links. We've got links throughout the world, but for this plot, I just pulled India. This was pulled just a few hours ago, and it's looking back 1 year worth of data for all live traffic flowing across the link. So each dot's a link, and then this blue line here is the estimated average performance based on the average across the US over the last decade using visibility sensor. So you'd expect the performance to follow this blue line, and it does for the most part. There's certainly a few outliers. A lot of those are just based on tower mount conditions. Some are mounted in locations where fog rolls in regularly, or some are just based on power outages. But this is taking every single data point over the last year and looking at the availability. The key outlier down here on the bottom, this one is a recent link that was deployed. And we found that the installation site was not up to our criteria. So typically we try to mount to telco type towers, but you can see that that this one is not a ideal tower and not a ideal location in terms of conditions either. It's a very windy site. So certainly learning from that one, and we'll change that location going forward. And I should say too, with this is just looking at the walk performance. If you take the walk plus RF, then all these availabilities push up to close to the 100% with the trade-off of the data rate. So you move from the 20 gigabits per second to whatever the RF limitation is. So 400 megabits or gigabit or whatever you have for the RF antenna. Okay, and so we have other tools available as well for looking at availability across the world and for localized availability within regions. And this is a nice map where red is good in this map. So all the red areas are showing availability 99% or higher. And you can see and this is based on a 10-kilometer link. You can see that there's a lot of locations within India, certainly within Africa, even the US, and a lot of good spots where we can, based on visibility data, you can reach that 99%. So this is the data pulled for this plot is from airports pulling the visibility sensors from each of those locations over the last decade. It can also do localized estimates as well. So before we deploy a link, we'll look at the estimated availability over the last 10 years for that physical location based on the nearest airport. Okay, and so to look at some of the deployments, so this is a great use case where it's walk crossing a challenging physical domain, a challenging or physically challenging obstacle, and this is in the Congo River, which is the second deepest and I think, or maybe the deepest and the second fastest river in the world, but one of the more challenging locations to cross with fiber. So these two towns, Brazzaville and Kinshasa, required 400 kilometers of fiber to connect the two cities. And because of that challenge, the data rates were nearly 8 times as much on one side of the river than the other. So we took a couple of the walk terminals, made a 5 to 10 kilometer link across the river, and that link has shown great results in terms of utilization and in terms of availability. So almost 3 nines of availability on the link, and data utilization between 5 and 10 gigabits per second typically. So it's kind of a great use case of walk crossing physical obstacles that are challenging for fiber. Another good use case, so this is in India, and just looking at a nice mixture of RF and walk and fiber, we're able to extend some of the fiber backhauls. So you can see the combination of the walk in red versus fiber in yellow, and then RF in blue. But with this combination, you're able to extend some of these fiber connections to towns that are currently underconnected, and it just shows that the walk isn't a complete solution, but it fits nicely into the overall network architecture, and we've found a lot of different use cases like this. Okay, so just a quick recap. So TARA currently has 20 gigabit per second technology. We've manufactured hundreds of these links, deployed around the world, typically 2 to 20 kilometer distances. We've got a lot of good data from these links and a lot of good performance metrics over the last few years. We've got a tracking system and modem that we've spent a good amount of effort optimizing for this free space channel that we continue to evolve on, and have some of these next generation capabilities coming out that involve some of the feed forward type mechanisms for the higher dynamic tracking, and then rate adaptation for extending the sensitivity and further improvements on the availability. So with that, just conclude with saying, we're definitely interested in any sort of collaboration. So if there's folks out there working in this space that with any sort of overlap, definitely reach out to me, reach out to folks on the team. But always looking for opportunities to collaborate, and thanks for having me, and let me know if there's any questions.
Thank you, Mr. Devin. Thank you for, I can understand that it is an odd hour for you because you are addressing us from USA. So thank you for all the pain you have taken. Any question from Mr. Devin? Anyone having any question may please raise your hand. Okay, so let us proceed to our next speaker. Our next speaker is Dr. Nagendra Nagaraja, founder and CEO QIPAI, and he will be delivering talk on quantum photonic processing.
Yeah, thanks a lot, Siddharth. So basically today we'll be talking about quantum photonic processing, optical processing. So basically there's the two combinations here. One is the communication, the other is quantum computing itself. Okay, so before we go there, I'll just introduce what we do. Okay, so we are a group of companies which is forming quantum technologies across the world, and we are a leader in quantum and AI and materials. We have 5 subsidiaries. QPI is one of them, and we have QPI Cloud, which is building cloud computing, and SuperQ is building a superconducting device technologies, which include single photon detectors, sources, and superconducting tapes for nuclear fusion. And we have Ulta, Kipai Ulta, where we're building quantum batteries and also solid state batteries based on quantum technologies. And Kipai Sabi is building photonic based silicon photonics based AI processor, which we expect to be at least 50 to 100 times faster than GPUs. So today we're talking about quantum photonic processing here. And I will first go through the use cases of quantum communication, and then we introduce the technologies we are working on and their application. So, like all the communications we saw, like in previous sessions, there are a lot of optical communication applications, and the way it can be deployed across the world. And one of the upcoming communication technology is the quantum communication. Okay, so what we have is a roadmap from now 2015 to 2035. We will be having a revolution in communication based on quantum technologies. And this involves your basic atomic clocking into the quantum link and quantum internet, and of course, universal quantum computing and quantum sensors. So some of the use cases of quantum technologies overview is like we have quantum computing, which is like applying quantum mechanics to perform computation, and then quantum simulation, which is possible now based on HPC, and then you have quantum sensing based on the quantum sensors. It's very important. Quantum sensing is one of the biggest areas which can benefit in meteorologies and a lot of other application, and quantum communication, which is the topic of today's discussion. So quantum communication is like there are huge applications, and we have a timelines here. Like for example, in 3 to 5 years, we are talking about QRNGs, and then like Department of Telecommunication, they can adapt a lot of these things in defense and communication, and then there'll be financial network, and then the corporate networks, general communication, and soon there will be in 10 years there will be a cloud-based quantum computing and communication as well. And we'll have a quantum sensor network, and we'll have a satellite secure communication based on quantum computing. And there's a huge market for this, and we are the leaders here. Kipai Group is a leader here, and we are working on commercializing most of these things. And what is the biggest threat for communication today is the security. And when quantum computing becomes really the mainstream, most of our securities, communication security will fail. And so that's the reason we have to move to quantum secure communication, and that's possible with quantum technologies, with the aid of quantum technologies. And when will be a quantum computer capable of breaking this? It's very soon. I think in India we'll have very soon 25 qubit machine, and very soon we can even have working towards the feasibility of 2K qubit machines that can easily break all the encryptions. And that's the reason we have to move to a really quantum secure communication. And some of the use cases of quantum communication is you have QKD, which is a standard one, and you have distributed quantum computing for cybersecurity, financial modeling, and drug discovery. QKD is like quantum key distribution network based on which we can actually really create quantum secure communication. That's one of the applications of quantum computing in communication. And you have quantum cloud computing, which is already there with Bracket and Azure Quantum, and this is going to get really deeper penetration, because we are seeing when we talk to our customers, which are large utility companies or oil and gas field or maybe financials, they are very interested in moving to really quantum computing and applying this to quantum communication as soon as possible. And then we have other applications like ultra precise and ultra secure quantum clock or GPS. This is one of the biggest applications of applications in the quantum communication, because this can give us both the defense and financials very secure communication. Okay. So these are some of the use cases where quantum technology can aid in communication right now. And a few more use cases in the banking industry where security is absolutely critical. I know a lot of banks are very interested in forming a data center with quantum security and safeguarding their business data, and then the credit card data, and then we have government and defense who really are interested in forming this quantum communication, quantum-based communication, so that it's very secure. And then protecting the asset from in the remote data centers. So most of the what pandemic taught us is remote working and remote accessing the data center remotely is very important. And there may be some of the digital assets which are very sensitive for this kind of access, and that's where quantum communication can help. And apart from this, the use cases, real life use cases are something like this, which in our defense department, DRDO has already implemented quantum key distribution technology, and they have tested it very soon. And China has implemented, and of course, US has implemented a lot of these things, especially DARPA. Okay, so what we have is we need to provide this terahertz transmission that will set the backbone for 6G. And that is possible. That requires some kind of a security that quantum communication can provide over optical fibers, and this should be exceeding 600 kilometers in a range. And for these kind of applications, the critical part is quantum repeaters. Not only the quantum key distribution network, there are other parts like single photon source, single photon detectors, and then you need to have a quantum repeaters. These are all hard technology to solve. So these technologies should enable us having this kind of data transfers, and also like in India we can secure a data transfer for elections. Okay, so that would make it very, very safe. Okay, in all over the world for all the democracies. Okay. And these are the overview of quantum application in the communication. I'm going to now talk about the deep technology what we are developing here to enable these things. So to enable these things, we do require quantum communication network, and there are parts in quantum communication network, as I told you, like single photon detector, single photon source, and photon repeaters, and that should enable quantum networks. And to process at the edge or at the cloud, you do require quantum computing. So with these two technologies, which is like photon sources, photon detectors, and repeaters, and then the quantum computing, we should be able to enable the quantum communication or photonic processing, quantum photonic processing. These are all in light. All communications in quantum computing is through photonics. Okay. So what we are doing to enable these things is we are building quantum computer among 5 subsidiaries. Skipai is one of them, which is the oldest subsidiary, and we have a lab in Bangalore, and we are building quantum computer here, and we'll be having the most powerful quantum computer in India in this lab very soon. So how does quantum computer look? It's something like this. This is a representation of bits, and this is how qubits are represented, and that's why it is more powerful. It can represent more information here. Okay. So what we are building basic processing is a 3-chip solution. We have a classical universal optimizer chip, which is called Trion. We already built on FPGA, and then we have a control chip. This control chip is a major innovation we have. This can control any type of qubits. It can be ion-based, or it can be superconductor or spin-based qubits, and it can be also based on diamond vacancies. This is a very scalable chip what we are building here, and this should help us scale to 2000 qubits very soon. So this year the plan is we'll be having 25 qubits, where we are setting up a lab in Bangalore, and we'll be able to have a test bed, TR4 of these test beds, which is 25 qubits based on superconductors. And we will be demonstrating this entire chain, which should be aiding in quantum communication and quantum computing. And this is a lab setup we have where we have a software called Skipai Explorer, and with that application can be developed. And then we have a circuit generator and a pulse generator, and we can actually put it on the cloud. We have our own cloud computing, which is Skipai Cloud, and we are going to put 20 qubit quantum simulator there. And there will be a control electronics, which we are building a room temperature control electronics based on FPGAs right now, which is available for sampling with some of the customers. We are also working with Oxford University on this. And we will be able to demonstrate spin qubits and superconducting. The spin qubits part is what we are researching right now, and superconducting qubits we are just demonstrating with 24 qubits. But our core area of research is in spin qubits, where we believe that we can scale it to 2000 qubits. That should help in a lot of this application in communication as well as processing. And this is a simulator what we have built. This is the WordCast simulator. You can do the circuits. You can simulate until 2000 qubits. You can, but the processing will not support. So you can do only until 10 qubits here. And this is available right now for researchers to actually use this test beds for various applications. Most of our customers are using it. And this is how we are planning our entire stack of the control plus transpond qubit that we are building in the lab. So basically, our control is a room temperature control. Basically, we have collapsed a lot of this control logic into one board, one FPGA board, and then we have a readout and read-in, which is in the cryogenic temperature, that is 42 Kelvin. And we will have some of these controls which will be working on 3 Kelvin. This is where you saw the fridge there, the quantum compute. That's how it is housed. And then we will be having a superconducting qubits, 25 qubits, that will be working on in 10 millikelvins. Okay, so this entire setup is being made, and it's just a matter of few months that this will be up in Bangalore. So this is the entire stack what I talked about, and this is put into a box here, which we are calling QPI Sense, QPI Sense, and this contains 3 FPGAs, and then we have analog in, analog out, and we have drivers, and they should be able to control these two kind of qubits. This is a spin qubit, and this is a superconducting qubit based on tuners, and we can do until 16, but we are doing until 25 right now. And this is the characteristic feedback latency is 100 nanoseconds, less than 100 nanoseconds, and trigger to ADPG pulse is less than 40 nanoseconds. But we are trying to reduce this latency for some of the application. We want to, once we have our chip for the control chip, this is again the control is through FPGAs, so it's a rack mount electronics, and the latency is expected. But once we have integrated cryogenic control, this latency will come down drastically. But this is good enough for testing a lot of this communication application as well as the computing application. And these are some of the expected the measurements what we can see, control and readout, both of them. And this is comparable to any other like Zurich instrument or any other control logic. So what is available commercially. And this is the actual board what we have, and these are some of the experiments what we have generated, actual waveforms that is generated from the board. And then so this is a protocol stack what we have. It runs on Linux, and we will have a control readout memories and QPI Sense control processor. It can generate, can emit pulse optimizer, and it can also do quantum error correction, and it can also generate waveforms, waveform memory. Okay. So this is available today, and we are building the entire lab around this, and we will be actually putting 25 qubits to control, and we'll demonstrate the entire lab setup. So this is again the actual circuitry and what goes into the box. We are putting all these things into this box, and then including readout electronics, and this one will be in the fridge. This is a room temperature, and this one will be in the dilution fridge, which we are working with Glucose to put this dilution fridge in Bangalore. And this is the superconducting qubits we are designing. So this is overall setup what we have in the lab, and we have the measurement database and Q codes. And again, we have to see that we'll be using extensively this machine learning to control the qubits and to tune the qubits. That's a very important IP what we have. And also we will have this up converter and down converters. We can also put it inside the box, and we can control pretty much any kind of qubits. It can be, and we can also control superconducting nanowire. There's another product what we are building, which is already fabricated. Few layers are fabricated, and it should be available with customers, even with Department of Telecommunication. It should be available by early next year. This is a very important piece of hardware for quantum communication and quantum network. So everything can be controlled by this particular thing, this particular box. Okay. So basically, what we have built is we have built typically for entire stack. The software stack is on hardware and entire system for both quantum computing and quantum communication. And this is how we can stack up. We can stack up these multiple boxes to actually control the qubits. We can do it as much as 100. We're planning to do as much as 2K qubits, which can aid in a lot of this encryption and as well as quantum computing applications as material discovery and other applications. So this is a lab what we are building right now, which is getting shaped. As I talked to you, they're already constructing this in a room. Okay, so the procurement is in the place, and we have this hardware already done. We're giving it to Oxford University very soon. And then this 25 qubit is most powerful quantum computer in India today. And we are creating 3 to 4 qubits in Bangalore, and it will be available for most of the research institute as well, which we are collaborating with, especially ISC and IIT Kharagpur. and of course Department of Telecommunication as well. They can also use this. Okay. So yeah, this is the lab available. And now moving to, we talked about quantum computing now for so far and what we are doing there and how we are enabling one of the most powerful quantum computers in India. And also how is it available for ecosystem, including Department of Telecommunication and institutes where they can do a lot of experiments on this. And now coming to quantum communication itself. So if I need to enable quantum communication, we require three pieces. One is of course software protocols, and first is then the single photon sources, single photon detector, and repeaters. These are all very hard problem to solve, especially on the performance side. So SuperQ is another subsidiary which is working on, and what is important, we are working on different superconducting products, including STS states for nuclear reactors, and cables, which are working with a lot of electrical institutes in India and abroad, and magnets again used for nuclear reactors, and the motors for automotives. This is a long-term motors is a long-term thing, but this is what is important for communication. Single photon detectors are the building blocks for quantum communication. Without actually having a real single photon detector, it is very difficult. It's not possible to build any quantum communication. So basically, this is what we are doing, and quantum communication can be enabled when we have a very cutting-edge superconducting technology combined with communication technology. That's how we can enable quantum communication. And as a company, SuperQ is building all these things. It has really built up an IP, deep IP for processing this or manufacturing the single photon and other superconducting devices. And also, it is actually working on discovering newer material that can go into this direction where we can get higher temperature operating. It's important not only the single photon detecting technology, but it should be commercially viable. If you look at current single photon detectors, are very bulky, and doing a large scale rollout is very difficult. So that's what we are solving. So typically, the single photon sources, the different applications are QKD, of course, and metrology, quantum computing with photons, and two random number generators. So what we have is important consideration here is on demand and are only probabilistically. So there are two kind of single photon sources, which can be deterministic or probabilistic. So we're still working on a probabilistic quantum sources, and we're trying to put this on a chip. This is the hardest problem. So this we are not targeting until 2025. But single photon detector is out this year. The reason why single photon sources are very difficult to build is because we need to have the manufacturing facility, which requires even if you look at an MV machine, that itself is a very complicated, and there are not many single photon sources across the world. So this is something we are building, and roadmap is 2025. This is how the setup is, but we are putting this entire thing in a chip, in a single chip, something like this. Okay, and then these are the things that goes on in the chip, and we want to actually scale this with miniaturizing most of the optical components, as well as making sure that this can be integrated in a low-cost setup, so that we can enable the quantum the quantum communication. And then detector. This is something we have now. Okay, single photon detector is something we have built, and it is actually getting manufactured now as we speak. And these are some of the performance. This is one of the best performance in the world today. Okay, and this works in the telecom wavelength. Okay, so there are different wavelength it can work, but we have different products for that. But it can work in telecom wavelength, and this can be a building block for quantum communication. Lot of this. Quantum networks does require this to actually enable the quantum communication. And the same technology.
Dr. Nagan, sorry to interrupt. Just sir, we are running short of time. So in PPT, whatever you find means something can you skip, please proceed. Just whatever portion, if you want, if you think that this can be skipped, then please take care. Just
sure.
Time, sir. Yes. Thank you, sir.
Sure.
Please proceed, sir.
Sure. So this is a single photon detector what we have, and this should enable the optical quantum processing. And these are some of the efficiency or the numbers we have. It should be available by August 2022. And these are different variants what we have. Basically, the one which is working on telecom wavelength is this one, the X1, and this can actually be deployed in most of the telecom applications. And these are some of the other applications of single photon detectors. Okay, so it can be used not only in communication but for other applications also. And this is a setup for quantum communication where single photon detector plays a key role. One is the QKD systems, and then we can just deploy all across these systems, and it also enables quantum internet and network. Okay, and it also can be used for the space application. It can be used as LiDAR, which gives you improved depth resolution and smaller pixels. Okay, and that's one of the application, photonic communication application it can enable. Healthcare, of course, we can skip this. Okay, yeah, so that's about it. Thank you.
So thank you, Dr. Nagendra. If any question to Dr. Nagendra, you may please ask. Anyone having any question to Dr. Nagendra? Okay, so let us move to our last speaker of the session. Our next speaker is Sri Subhendu from Wi-Fi Dabba. He will be delivering talk on free space optics. And Sri Subhendu, he is co-founder of Wi-Fi Dabba in 2017. The Wi-Fi Dabba has deployed around 1,000 public Wi-Fi hotspot at micro retailer to accelerate the transition to digital India. The company is working a lot to bring all the retailer in the digital domain, and they have made a very good contribution to push digital transaction across the country. So over to you, Subhendu sir. Please proceed.
Thank you, sir. My screen is visible?
Yes, please.
Perfect. All right. Thank you for this opportunity today afternoon. I know I'm the last on this speaker list today, and it's almost lunchtime. I'm not going to extend. I'll try my best to cover in the next 7 to 8 minutes. So let's get started. So what I'm going to be talking today is about a real case study that we have been building the FSO network in Bangalore. And I'm going to talk about the real life learnings and why we choose to work in the free space optics space. So these are the 3 things that we will cover quickly. Why this technology makes a compelling use case in real life in comparison to LTE and as a 4G solutions that what we have. We would cover briefly what we intend to do as a company and why we are building using FSO. So to talk before in detail why we jumped into free space optics, let me give you a little background of our existence. So back in 2016, we started working trying to build a public Wi-Fi mesh in city of Bangalore. The goal was to provide affordable sachet size internet access to underserved people in the city where this was pre-Geo era, pre-4G penetrations were not this high what we see today, and data pricing was very high. Over the next 2 years in 2016-17, what we realized is as the adoption of mobile phone was increasing and the 4G penetration was increasing, this was not sufficient for average user in this country to buy a 300 rupees per month prepaid instrument and consume 1 GB, 1.5 GB of data every day. If you look at the average consumption consistently, it has grown over the last 5 years. And the experiments network that we built in 2017 taught us that network cannot be built in this country because of the unreliable and patchy network, the fiber network that Bangalore offered, the incompatible devices, non-SIM based devices, which were not able to connect to internet, the limitation of data, and of course the unaffordability part of the whole 4G infrastructure that provides. So these were some of the early learnings that we have had in 2017, and we had to acquire a license in order to deploy this network and work with few hundred local cable operators and larger ISPs in order to build this network, but it could not just scale. So in 2018, we had to look for alternatives in order to build a network that could basically be built from scratch, because of the major reason being the underlying cable, underlying optical network in Bangalore city, a city like Bangalore, was not sufficient in order to build a public infrastructure on top of it. So what we realized is if we need to build and scale this infrastructure, we need a low-cost fixed wireless access system that can be built on top of open source technology and open spectrum. So these were the learnings that we had in our initial year as a startup from deploying this network of thousands of public Wi-Fi hotspots. What we realized is if this has to grow, we need to find alternatives. We started working on point-to-point 5 gigahertz devices, but they were not scalable, as other speakers have already discussed those. It is just not, RF is not scalable. You can't build a citywide Wi-Fi mesh based upon that. We looked upon other Li-Fi technologies. We worked upon other stuff, overhead fiber and stuff. Again, unreliable, and cost does not justify deploying those solutions. Eventually, PM Vani came along. Srivastava, so we have been working very closely during his TRAI days, and that came in, and that got us rid from the ISP license. It makes an even more compelling use case to build this network out using a technology which is scalable, which is future-looking, future-proof, and that's where we ended working in free space optics. So what started as experiment back in 2018, we deployed our first free space optics in association with Tara in 2019 in suburbs of Bangalore. So before we move into that and understand what are the what use cases it solves, I want to run you through the. I'm sure you guys, everybody knows about this structure, but this is our personal experience. I want to share how we were trying to deploy this and pre-FSO technology, and how we have innovated and what we have done in both cost and network optimization using free space optics. So if you look at the delivery mechanism, you have undersea cables, then you connect to an NLD line. Middle mile is generally underground fiber within the city, which connects to your POPs. And then you have the ISPs that manage the last mile connectivity using overhead fibers or point-to-point connectivity. So if you look at the cost structure, that what we have observed in the last 3-4 years of our existence, the different cost structure, if you look at 30 to 75 paisa per GB is your subsea cable fiber cost, that eventually is your landing cost. You have a 20 paisa cost for your NLD. The highest cost is your middle mile and last mile. This is predominantly because of the cost of underground fiber and the operating cost that is involved in order to manage those infrastructure. So what we realized in our journey is, if we have to innovate, this is the space where we can really innovate and bring down this cost and give a better both experience, speed, and a better pricing to our consumers. So this is the core learnings over the years that we have had. What we do now currently, and we are trying to build over here, is a stack that can deliver an end-to-end connectivity for our consumers. So what you see on the left side of this screen is a map of Bangalore. What we have essentially done over here is divided city into a grid of 2x2 grids, square kilometers, roughly around 4 square kilometers. Each unit has its, each grid has its own laser device, which basically becomes a backhaul servicing for this particular area. What we call this as middle mile laser grid. Each other connects to each other POP and forms a redundant network over here. We have our own proprietary last mile stack, which is basically router OS and our double OS stack, which caters to the last mile connectivity. It forms a mesh network. This basically works in conjecture with the PM Vani framework. Then we have a layer of the double monetization platform, where we basically the entire AAA stack sits. You have your other monetization layers that comes into picture, how our partners are paid out, and the entire stack sits over there. And of course, the policy framework that PM Vani offers. So what we call this entire stack is a ISP in a box model, where we essentially creating a self-serving platform where anybody could take this stack from us and deploy in their regions, towns, and community. So what you look at the last mile stack, router OS and double OS, we have open source the most of the stack, where people don't have to pay us any licensing fees over here. And we continue to build affordable lasers, which would in coming days be made in India and would be made available at a very affordable price points. So this is what we as a startup are doing in this space. So if you look at the POPs, out of 100 POPs that we envision to deploy in Bangalore market, right now we have around 22 POPs which are live. There are live traffic what these POPs are carrying with serving thousands of users each day. Moving on to the next slide, what you look, this is one of our own units that we have built. The photograph that you see, this is deployed in an area called BTM layout in Bangalore. This serves 1 Gbps link. This is a free space unit, optics unit that has been homegrown, built by Wi-Fi Dabba. As I was talking about the benefits, if you look at the clear-cut benefit from what underground fiber offers, the upfront cost gets reduced. We are able to deploy at under 3 lakhs versus a 25 lakh per kilometer pricing that you see if you were to do it in Bangalore. We take care of the time. There are no ROW issues involved. It could be very quickly deployed. Maintenance-wise, it's pretty easy and straightforward. We continue to build tools to self-monitor the devices and use motor optics to basically auto-align these devices. And of course, this is super scalable in terms of deployment for the region where the weather is supported and the geography is supporting. So this has enough capacity, in fact, more to offer both to build your micro CDNs as well as build use cases for edge computing. The goal is to build hyperlocal CDNs going forward, where the lot of OTT content can be delivered at the edge itself, which will eventually improve user experience and bring down a lot of cost structures as we move ahead in this rollout. To summarize, as I promised, I would keep it short. We are a full stack software company which is trying to innovate in order to lower this deployment cost. At the same time, we continue to adopt to new technologies. Free space optics is a very promising technology that is going to solve a lot of 4G, 5G use cases in terms of bringing the towers which do not have fiber connectivity. FSO fits very well in those use cases as well, and we continue to innovate over here. As promised, I'll keep it short. Any questions, I'm happy to answer.
Thank you, Subhenduji. Thank you very much. So any question to Subhenduji, please. Anyone having any question, you may please ask. So I think with this, we came to end of our today's workshop. So I, on behalf of NTI Plit, and I thank all the speakers for giving a wonderful talk, and I also thank all the audience who have patiently listened all those things. So with this, we come to an end, and at the end, I would like to thank Sri UK Srivastava sir, Director General NTI Plit, and our DDG sir, Sri Raju Sinha sir, who have been both of them have been the guiding force behind this workshop. So, sir, if you allow, we can end the meeting, sir.
Yes,
and
yes. We can close the meeting. Thank you.
Yes, thank you, sir. And please write down the contact number. My email ID is there. DDG sir email ID is there. If you have any query after this workshop also, then also you may ask. So you may write number and email ID both. We will be happy to answer. All these speakers are in regular touch with us. If you have any query, we will contact the speakers, and we will let you. We will provide you answers. Okay. So thank you. So with this, we come to end. So now I am. Okay. Now we are ending the meeting. Thank you, everyone.